In this lecture, we're going to talk about the post-main sequence evolution for low-mass stars. What happens to these stars when all the hydrogen in their core is exhausted?
Now, low-mass stars are defined to be stars with masses less than roughly 8 times the mass of the Sun. The reason for this distinction will become apparent in a little bit. So let's take a look at the very core of the star. So this is just the core of the star, and all of its hydrogen has been converted into helium. At this point, the core stops producing energy. It is no longer fusing hydrogen into helium, and therefore there is no radiation pressure being generated in the core. Therefore, gravity causes it to contract and heat up. The layer surrounding the core also contracts and heats up, and it heats up enough to actually start fusing hydrogen into helium, this time in a shell around the helium core. The outer parts of the star expand because the star's hydrogen burning layer is producing more energy than is required to balance gravity. That's because the hydrogen burning shell has a much larger surface area and contains more material than the core did. So the outer layers of the star begin to puff out, and they continue puffing out, and as they puff out, they get cooler. You can think of it as the atmosphere is having to do work against gravity to expand, and that cools the star down. Since the surface becomes cooler, the star becomes redder. We call the star at this stage of its evolution a red giant. Now, the atmosphere puffs out a very large amount. If this is our sun on the left, then this is the size of the red giant that the sun will become, roughly an astronomical unit in radius. So it will puff out right out to the radius of the Earth. So in the future, in 4 to 5 billion years, the sun will go from having a hot core and a warm surface and a small size to a very hot core, a much cooler surface and a much larger size. However, because the core is hotter and the hydrogen burning in the shell is producing more energy, then the luminosity is greater. So the luminosity actually increases. So what happens next? Well, to understand that, I need to talk briefly about so-called degenerate gases. We go more into quantum degeneracy in our quantum physics class. So I'm only going to sketch out the brief phenomenological details here. Degenerate gases are what happens when you either squeeze a gas under extreme pressure or you cool a gas right down to extremely cool temperatures. In our case, in the astrophysical case, the matter inside the very core of our red giant is being squeezed to very high densities. In a normal gas, if you compress it, the particles will start moving faster and the pressure and temperature get increased. You see this when, for example, pumping up your bicycle tires. And when you heat up a normal gas, again, the pressure increases. If you heat up a balloon, it will expand. But for a degenerate gas, the particles essentially have nowhere else to move. They cannot increase their energy in particular. They are said to occupy all of the available energy levels that they can occupy. This is a little like an atom in its ground state. All the electrons in an atom in its ground state occupy the lowest energy levels, the lowest electron shells. And once that happens, you can't fit another electron into that electron shell, into those electron shells. If the whole gas is in this state, then when you compress the gas, the particles cannot move any faster. They simply wiggle about more energetically. So if you compress a degenerate gas, the temperature increases, but the pressure remains the same. Also, if you heat a degenerate gas, the pressure stays the same. So once the very core of our red giant star becomes degenerate, we've lost our positive feedback loop. Before, when you compressed the core of the star, it heated up, that increased the pressure, which allowed it to balance the force that was compressing it. But once the star becomes degenerate, heating up the matter doesn't have any effect on the pressure, so the core will continue contracting. This leads to what is known as the helium flash. So matter in the core is fully ionized. All the electrons are completely free of their atoms. Most of the pressure in the core comes only from the electrons, and as the core of the helium ash shrinks, the ash from the hydrogen burning, it becomes degenerate. Its temperature will increase, but its pressure will remain the same. The density rises to about 1 million grams per cubic centimeter. That's about 1,000 tons per cubic centimeter. The temperature keeps going up, but as it passes 100 million degrees Kelvin, helium atoms can overcome their mutual repulsion and begin to fuse into carbon-12. It takes 3 helium nuclei to fuse into carbon-12, but when they do so, they release a very large amount of energy. So eventually, the core heats up to such extreme temperatures that helium ignites and produces an enormous amount of energy very quickly. The temperature rapidly rises, but the pressure stays the same. The core cannot respond to the increased temperature by expanding. So the temperature increases and the helium starts fusing at an ever larger rate. The increased energy production then increases the temperature, which increases the fusion rate, which increases the energy production, which increases the temperature, and so on. You get a runaway nuclear fusion reaction in the core, analogous to this. Essentially, you get a colossal nuclear explosion in the very core of the star. This is known as the helium flash. For a few minutes, the core generates 100,000 billion times more energy per second than the sun. That's 100 times more energy per second than all of the stars in the Milky Way combined. Remarkably, this does not destroy the star. The energy is absorbed in the outer layers. The outer layers, remember, are puffed out so much that they are able to absorb this colossal explosion that is going on underneath. There is no outward sign massive explosion has occurred in the core of the star. The helium flash only occurs in stars between 1/2 and 3 times the mass of the sun. After a few minutes, the core becomes so hot that the gas becomes normal again. The degeneracy is lifted. The new carbon nuclei that are being produced are so energetic they no longer remain degenerate. The pressure can then increase again and stabilize the star. At that point, the star settles down to the following structure. You now have helium that the core of the star remains hot enough to burn helium, so helium starts fusing into carbon and also oxygen. The shell surrounding it, where hydrogen is burning to helium still, that's still there, and you've still got this very large, cool envelope. The extra energy from the helium fusion causes the core to expand, and this forces the hydrogen burning shell to expand as well. The expansion cools the hydrogen burning shell, and because it cools, it absorbs heat from the surrounding envelope to compensate, and that causes the envelope to shrink a little and get a bit hotter. So what happens when a star moves through this sequence of stages in its life? What happens when you follow it on the Hertzsprung-Russell diagram? Well, hydrogen core burning happens on the main sequence. This blue band from top left to bottom right is the main sequence. The red line here are where stars lie when they are initially born. Okay, so let's take our representative star, which is born on the main sequence at this position here. Throughout its main sequence lifetime, which is 90% of its total lifetime, it just burns hydrogen in the core, and it gradually moves a little way from the bottom to the top of the main sequence. Remember, stars do not move up or down the main sequence, they just move from one edge to the other. Once the hydrogen in the core is all used up, the star begins moving on this trajectory here. This is called the subgiant branch. This is the period of time where there is no fusion occurring in the core, but there is hydrogen shell burning around the core, and the star is beginning to expand. The star moves down the subgiant branch and then starts moving up the red giant branch as the outer layers start to expand more rapidly, as the inner layers of the star, the core of the star, begins contracting more rapidly and heating up. Eventually, you ignite helium in the core. For stars less than 3 solar masses, it gets ignited in a helium flash. If they're above 5 solar masses, it gets ignited before the star's core becomes degenerate. The star then rapidly moves down here and onto the so-called horizontal branch. On the horizontal branch, you have a helium core in which helium is fusing into carbon and oxygen. Surrounding that, you have helium ashes, and then surrounding that you still have the hydrogen burning shell. Eventually you move up along the asymptotic giant branch. This occurs when the helium in the very center of the star is now used up and you just have carbon and oxygen ashes. This is surrounded by a helium burning shell, which is surrounded just by helium ashes, which is surrounded by a hydrogen burning shell. As you move along the so-called asymptotic giant branch, you finally move up here, and eventually you start moving up here and onto the next stage of the star's life. During that final phase, where you have carbon and oxygen ashes at the very center, the star puffs out again and becomes a red supergiant. Now, stars less than 8 times the mass of the sun end their lives at this point. They are not large enough for their gravity to contract the core and heat it up enough to start burning carbon and oxygen. So what happens is the outer layers keep expanding and expanding and will eventually drift off of the core of the star. So the star ejects its outer layers, and the star rapidly moves along this path here on the main sequence, down here, and the exposed core of the star gets left behind. This remnant core no longer has fusion reactions occurring inside of it, and it slowly cools down and becomes what is known as a white dwarf. So to summarize, for low-mass stars, let's take our Sun as an example. Our Sun will spend about 9 billion years on the main sequence. We're halfway through that now, burning hydrogen into helium. It'll spend about 1 billion years as a red giant. It'll spend about 100 million years as a yellow giant. That's on the horizontal branch, where you're burning helium in the core. And then about 10,000 years as a planetary nebula. A planetary nebula is the name given to the stage of the life where the star is ejecting its outer layers. It's again one of those many names in astronomy that is confusing, It has nothing to do with planets. A planetary nebula is what is the name given to the appearance of a star that is ejecting its outer layers. Once the outer layers are gone, the exposed white dwarf is left behind and simply sits there and cools. Again, just to remind you of the various branches on this diagram, after leaving the main sequence, the star will move up the subgiant branch, then will move up the subgiant branch and onto the red giant branch, then down the horizontal branch, and then up the asymptotic giant branch. Those are the names given to these 4 stages of post-main sequence evolution for a Sun-like star. The exact appearance of these branches of the Hertzsprung-Russell diagram differ depending on the mass of the star. This is what they look like for a 1 solar mass star, and we've already seen what they look like for a 5 solar mass star. The star will spend about 10% of its life as a red giant. One useful way to put the stages of a star's life into context is as follows. If a star lives for only 1 day, starting at midnight, then its main sequence lifetime lasts from midnight throughout the entire morning, afternoon, into the evening, and ends at 9:36 p.m, which is when the red giant phase starts. As I mentioned, planetary nebulae are the very last stage of the red giant phase when the outer atmosphere of the star is ejected. The ejection of the outer atmosphere creates incredibly beautiful nebulae, as shown here. These are all stars exiting the red giant phase, their outer layers drifting into space and leaving behind their dead core as a white dwarf. White dwarfs are the end result of all stars smaller than about 8 solar masses. And as I mentioned, they are the left behind core of the star, in which fusion reactions are no longer occurring. So those carbon-oxygen ashes are in the center of the white dwarf, and there'll be helium ashes with some hydrogen left on the surface in general. The white dwarf is supported by the pressure of degenerate electrons. As I mentioned, the star is extremely dense, and the properties of the star are determined by the properties of matter at subatomic scales. They depend on, particularly, the details of quantum mechanics. The size of a white dwarf is similar to the size of the Earth. Their radius is about 6,000 kilometers. They contain the mass of the Sun. Their escape velocity, to get off the surface of a white dwarf, you would have to travel at about 2% the speed of light. The density is a few million grams per cubic centimeter. If you look at them, they have a blue-white color. Their temperature is around 25,000 Kelvin at birth, and the white dwarf does not produce any energy of its own. It simply cools off. A white dwarf sometimes is referred to as a star. It's not really a star. It is what is known as a compact object. It is a stellar remnant that is extremely dense and extremely compact, which means there's a lot of matter in a relatively small amount of space. We will encounter 2 more, even more exotic compact objects next week.